the 10th colloquium in the series, and it's a pleasure to have Professor D.D. Sarma from IISc Bangalore with us today. And he didn't need much introduction because throughout years he has been quite a well-known name in the experimental condensed matter physics and material science worldwide. But just for sake of our young colleagues or the students, I would like to basically say a few things about his academics. So he did his integrated master's in physics from IIT Kanpur in 1977, and then he moved to IISc Bangalore in that year only, and completed his PhD under the guidance of Professor C.N.R. Rao in 1982. And then he remained in IISc for one more year and went to Center for Research ULIC as a guest scientist in 1984. And again, he returned back to IISc as a lecturer in 1986. And since then, he has been associated with solid state and structural chemistry unit of IISc through his various publications. And at present, he is serving that unit as a professor. And he has many awards and honors at his name. He is recipient of the Tawaz Physics Award in 2007, IIT Kanpur Distinguished Alumni Award, IISc Alumni Award, UNESCO Biennial Javed Hussain Award, Santi Swarup Bhatnagar Award, Knight of the Order of Star of Italy, Honorary Doctor from Uppsala University, and many more. And his research interests lie in various areas like the strongly correlated electron system, conjugated polymers, experimental electronic structure, calculation of various semiconductor nanoparticles, and so on. And today he will be talking about very interesting material, organic-inorganic hybrid perovskite, a wonder material. So without further delay, I would like to hand over the forum to Professor Sarma and again invite him to deliver today's physics colloquium.
Thank you, Professor Mishra, for the very kind and extensive introduction. I start with an anticipated situation for which I should apologize. My internet has been a little unstable, and I am in the full screen mode, so I cannot see anybody wanting to ask me a question, or if I drop out of the internet, I'll not know. But when I come back in, because it's unstable, then even if I drop out, I'll come back in very soon. Then you should sort of point out to me, please don't hesitate to stop me and tell me that, well, you couldn't be heard for the last half a minute or 30 seconds, please repeat it. And you can also stop me at any time if you have a question. And please do not hesitate to do that, simply because the internet being unsteady, I would like you to miss the continuity of the talk and therefore kind of not follow what I'm trying to say. As I was pointed out, and that it is a colloquium, and so there's a large presence of young students and young researchers, though I do see quite a few very experienced scientists too in the list. So I have kept a rather long introduction on this topic that I'm going to talk about. The title, as already announced, is Organic-inorganic hybrid perovskites, a wonder material. It is a wonder material in the context of optical activity. It has some very, very interesting optical properties in many different manifestations, and it would be impossible for me to cover all aspects. So I'm going to focus down a little bit and not talk about all aspects of optical activity, but only talk about its application as a photovoltaic material, because there itself, there's been such a lot of surprising results that it is still keeping the entire community of a very large community of scientists all over the world extremely busy in trying to not only improve the material properties and device functionalities, but also to understand the fundamental way why it is such a spectacular material. And this is what I'm trying to communicate to you, to give you a flavor of what this material is all about, why we're excited about it, what the open issues are, and what kind of way we personally, our group, is thinking about. Before I get on to it, let me point out the funding for most of the work that we do in general, and also related to this particular work that I'm going to talk about, comes from either ACRB, Nanomission, or DST, which are all Government of India funding through the Ministry of Science and Technology. It has also been funded, part of it, which I'll have occasion to talk about, is India-Austrian cooperation, that also was on our side, the Indian side, supported by DST. And a large part of our activity over the last 3 years was also supported by a private fund called the Jamshedji Tata Trust, and I'm very happy and honored to acknowledge their contributions. The plan of the talk is going to be as listed here. I'm not going to read it through because I'll take you through one by one, and I'm going to start with introduction. And as I said, that I have kept a rather long introduction, keeping in mind on the young researcher community, so that, and also the non-specialist in this field, so that I can communicate to you the most important point, which is, why are you so excited about this material? Why do we have the audacity to call it the wonder material? What is so wonderful about it? And let me get started with it. And since I'm talking about photovoltaic material, here is a crazy looking curve that you don't have to try to understand in detail. What it does, this is a particular data sheet that is being maintained by National Research Energy Laboratory in the USA, Colorado. And what is being plotted in the y-axis is the photovoltaic cell efficiency, and in the x-axis, the history of the evolution of how the cell efficiency of a given technology improves year after year. So this is the number of years. So if you different symbols and colors follow the progression of the cell efficiency over the years for a given technology. There are many different technologies, and that's why there are so many curves, so many symbols, and so many colors. Up here in the violet that you see are really not the commercial products. These are the ones with multi-junction cells and single-junction gallium arsenide-based cells, which are up here. And we're not going to talk about that. The more usual thing that we know about, at least the commercial application, is silicon-based. And this is the polycrystalline silicon-based, this square, open square line that you're seeing, how the efficiency is going up with years. The blue, the filled square, is actually the single crystalline silicon, how it improves. Since it's rather crowded, it's more difficult to understand how the efficiency is increasing. Let me help you by showing you an overall curve. This ellipse covers the silicon technology as it is growing, and this major axis that I have drawn for you in dashed line through this ellipse, which is slightly inclined, shows you the rough rate of increase in the efficiency over the years. You can see in the year somewhere mid-70s, the single crystal silicon had efficiency in the range of 14%, and in 2020, we are talking about something near 26%. So over these many years, which is roughly about 40 odd years, 45 years, we have improved the efficiency from 14% to about 26%. There is another technology that is important, which is called the thin film technology, which is given by these green symbols you can see over here. Their efficiency improved a little faster, and it's shown over here. Again, by the inclination of the ellipse and its major axis, you can see that it is inclined a little faster. So its efficiency improved a little faster, starting from somewhere near 6% efficiency, again in the mid-70s, and the latest that you have is in the order of 24%. So it is a saga of nearly 50 years of tremendous activity, tremendous scientific and industrial research at a very fundamental level that has gone into this improvement over the 50 years. And that has made these technologies now commercially viable. One has to understand how slowly the technology improves over a period of time to give us the efficiency that would make it competitive with more conventional sources of energy. And that's how the solar energy now is competitive. And this particular material that we are talking about, and that's shown in the next one, is this little phase over here, which is shown with the yellow dots here. That started somewhere in the 2010s. And in less than a decade's time, you can see that its efficiency has increased what for the silicon technology took us more than 50 years of improvement. And not only that, now it competes, and the best efficiency that we have is above 25%, which is above the polycrystalline silicon best efficiency that we have today. So this is a material which has shown a spectacular increase in the photovoltaic efficiency. The rate of increase has been fantastic, and also its eventual efficiency that you have got is fantastic. And therefore, it is a very, very wonderful material to talk in terms of photovoltaics. But that is not all. There are many other aspects of it that I'll be talking about in a moment that makes it very, very wonderful, because the technology to make the silicon single crystal solar cell is extremely demanding, requires fantastic technologies, very, very controlled situation to create the final cell. So the overhead of preparation or methodology of preparation is very expensive, both in terms of energy and cost. Whereas this particular technology, this wonderful material, one can make a photovoltaic cell without ever heating anything beyond a certain small temperature of 100 degrees centigrade or so. And most of the processing is done in the solution base. So in solution processing, which is economically much more viable, not requiring high end of technology, makes this system also extremely attractive from the cost point of view. So not only the efficiency increase and the ultimate efficiency, but its processability by the solution route also makes it a wonderful material. There's just a blow up of in that crazy, very crowded plot. This is the part that I'm talking about. And you can see right now it's sitting at about 25.5% efficiency, which is the highest starting from over these last approximately 10 years of history of the growth of this particular field. In fact, the growth of the field in the early days, it actually started with something that is known as dye-sensitized solar cell that many of you may know about, which actually started competing against the silicon solar cell. It was proposed as a competing technology to silicon solar cells. And that had the advantage is that one could make very thin film of this particular material, because remember, the thinner the film is, less is my inventory cost, also less is my mechanical stability and other factors. So there are some advantages of having a very thin film that can absorb very efficiently and give rise to the photovoltaic effect that I want and sufficient power and energy density. And this was based on some TiO2 mesoporous structure, which was coated with a sensitized material, which would do the absorption, which had good absorption efficiency, and that created the electron hole pair. And then that electron hole pair was quickly separated. One part went into the TiO2, that is the white part. The other part, the whole extraction, went into the other part, which is made of some other material, depending on which particular technology you followed. It had different materials. And the thickness of the early cells in the dye-sensitized solar cell that used liquid electrolytes was in tens of micron. Very quickly, this liquid electrolyte was replaced with a small solid-state device, and then the thickness of the device came down to about a couple of microns. And improving on that very technology, a lot of innovation took the cell thickness, what we call the extremely thin absorber, to a micron level. And the early use of this wonderful material that I'm going to talk about in great detail actually allowed in this particular architecture for the photovoltaic cell to come down to sub-micron length scale. And this was possible simply because the absorption property of this material is fantastic. So the absorption property makes this particular material extremely important for photovoltaic applications, as I'll show you further in subsequent slides. But there's a history. I said that the history of the photovoltaic activity on this is just about barely 10 years old. But the history of working of these materials to get them electronically active actually started with David Mixey, who was at IBM Watson Research Center at that time, way back in 1990s, when he was playing around with these kind of materials, which are called hybrid materials. They're called hybrid material because there's an organic part and there's an inorganic part, and it's mostly the halide ion that appears here, and here is the metal that appears, the AsP group metal, and that's why it's called a hybrid material. this kind of hybrid halide materials were used for making various kind of electronic units, transistors, as well as OLEDs by David Metzi way back in 1990s. But photovoltaic application of this particular thing really started with a Japanese scientist, Professor Miyasaka, who was working with these two particular compounds, methyl ammonium lead iodide and methyl ammonium lead bromide, and he was trying to make different kind of photovoltaic cells, and then the efficiency that he was reporting mainly in conferences in those days were very small and nobody took any notice of it, and that was in the early 2008. The first published result came from his group, Miyasaka's group, had a 4% efficiency, and it had very low stability, and so it didn't catch on still. First, reasonable efficiency was shown from Park's group in 2011 that showed a 6.5% efficiency of a photovoltaic cell, where these kind of materials, methyl ammonium lead iodide and methyl ammonium lead bromide, were used to sensitize TiO2 mesoporous structure, as I showed you in the dye-sensitized solar cell, to get this kind of efficiency. So basically, these materials were being used to absorb light, convert it into electron and hole, and quickly that electron and hole were separated into two parts. One part conducted away the electron, the other took away the hole and brought it to two different terminals so that externally they could be connected to drive a current, and therefore you could get electricity. But the main revolution started when Snake, and almost around the same time, the group from Gretzel's group showed that one could use these materials to get efficiency, photovoltaic efficiency, that went beyond 10%. There was this mental block that got shattered, that once it crossed 10% quantum efficiency of photovoltaic cell, everybody started looking at it, and then on the real revolution or tremendously fast development took place in this particular field. And the development gave rise to some very, very fundamental understanding about this material, as I shall show you next. The dye-sensitized solar cell that I talked about, which also was a structure that this paper that I just now showed from Michael Gretzel's and over here used, they basically use a structure made of, let's say, TiO2, mesoporous structure of small particles of TiO2, which is coated by this material, in this case, methyl ammonium lead iodide with some little bit of chlorine for reasons, magical reasons that were not understood at that time. And this is the absorber, and then a whole transported material. So the photon would be absorbed in this material, which is very, very thin, because it doesn't have to conduct the electron and hole. The electron would jump into TiO2 because of band alignment, and hole will jump into the whole transporting material. Electron and then will go through the TiO2 and come to the terminal, and on this side, this will go to the other terminal, and from externally you can connect it and get a current flowing through. But what Henry Snaith showed very soon, that you don't have to use TiO2. Instead of TiO2, you can use aluminum oxide. Now that's absolutely remarkable, because aluminum oxide has such a huge band gap. I said here the electron jumps in there because of the band alignment, makes it easy for the electron to go there. In the case of alumina, we know that the alumina, the electron cannot, because its conduction band is so high up, the electron cannot go into alumina here. So the electron, if it at all it has to go along this, the active absorber material, and the active absorber material itself must start to transport the electron, and the whole was conducted out this way. So this was the first observation that said that no, this is a fundamental different technology from the dye-sensitized solar cell, where the dye would be used only to convert the photon into electron hole, but it is not the transporter material. Transporter material was TiO2 on one side and the whole transporter material on the other side. This showed that it can also transport the electron. And in fact, this was very quickly shown that not only electron, you could make a structure. This is the usual structure that one would make for the dye-sensitized solar cell-like structure, where you have TiO2 for electron transport. This black layer is the dye, which is this methylammonium lead halide, and then the electron will go into TiO2, and this TiO2 in network will connect the electron, bring it to TiO2, and then it can be taken out from here. And the hole will go out that way. But instead of that, what this particular paper showed is that you can have a layer, a complete layer of this hybrid perovskite, such that not only the electron transport, but the whole transport also will take place through this layer. And they found enough high efficiency in this to point out that this is fundamentally different from the technology of dye-sensitized solar cell shown over here. This is not only a very good absorber that creates electron and hole, but it also is a very good transporter of electron and hole both, such that the electron goes this way, hole would go that way, and then you put an electron blocking layer there, which is the hole transporting layer, and you put a hole blocking layer and becomes the electron transporting layer, and you can tap out the electron and hole from this system quite easily. That means this has very good absorbing property and very good transporting property. So now let us ask the question, what are the fundamental aspects of this material that makes it so good, that it is such fantastic efficiency that it gives so easily? So in order to understand that, let us first remember, what is a solar cell? How is a solar cell constructed? How is the electron and hole generated, and how it is separated? Typically in a photovoltaic cell, a PN junction is created such that you have positive and negative potential on that side. Now imagine if an electron hole gets created anywhere here, what would happen is that electron will feel this positive charge and will go that way, and the hole will feel this negative charge and go this way, such that this PN junction provides a driving force, a potential gradient to separate electron and hole. And therefore, the electron would end up going that way, hole will come this way. Excuse me, sir? Yes, please. Go ahead.
So, please show your slide, sir. I can't see your slide, sir.
You cannot see the slide?
Yes,
Is that true for everybody?
Only your...
No, you have to just key on the presentation.
Okay, just a moment. Let me, thank you for pointing this out. I'll do it.
Actually, if you go and pin the other presentation, there are two DD Sarmas. If you pin the other one, then the slides come back.
Is it? Okay. I think that
for us, I mean.
Okay. Shubhro, I think that is instructing me, and that's very nice. Okay, your presentation, if I click.
No, we have to do it, Didi. I think you are fine.
Okay, Didi, in that case, so somebody else started presenting something. So if you now represent, I think it will come back.
Yeah, somebody else became a presenter, and after that.
Oh, okay. Now I'm going through the process again, and tell me when I say that I think I'm sharing it. Do you see it now?
It's fine. Now you can see it.
Yes.
Now you can see it? Okay,
yeah, it is
wonderful. Good. Let me get the razor pointer. Thank you very much for pointing this out. I really appreciate your intervention. So please do intervene whenever. Now can you see everything, everybody?
Yes, sir. Yes, sir.
Okay,
Thank
wonderful. Thank you,
so
because you pointed it out. I really appreciated that.
Yeah. So to see the slides, there is a sign of a pin. You should click on that pin. Then this in the entire screen, you will see only the presentation of Professor Sharma and nobody else.
Okay. Oh, that was not an instruction to me, right? Because I see.
No. It's not instruction for you. It's for the audience.
Okay. Fine. So please again stop me as soon as you want. I mean, because normal seminar giving, I can see the audience, I can interact with the audience, and I feel good. Here it is, I'm talking to my screen and I feel terrible. So if you interrupt me, I feel, yes, you are there, and I can feel it. Thank you very much. Let me continue. So I was telling you that a PN junction provides a natural way of providing a potential gradient such that if I create an electron hole here, the electron will go that way because it feels a positive potential that side. And if I create the electron hole this way, then the hole goes this way. So automatically electron and hole get separated, and then they have to drift to these electrodes, and then it drives a current outside. That's how a photovoltaic cell works. So with this rudimentary part, now I'm ready to tell you what are the properties that we want from our photovoltaics and what are the real properties that help me getting a high efficiency. It must be a good absorber of light. And let me tell you, silicon is a lousy absorber of light. And that's the reason why silicon, you need a thicker film, and thin film technology is a challenge to silicon technology because of that. Because silicon, for much of the solar spectrum that is useful and carries a lot of energy, is absolutely a lousy absorber. What about this material, as I'll show in a moment? So we need good absorber of light. We need effective separation of charge carriers, so I can provide this potential gradient, but then it has to diffuse, as I said. The electron has to diffuse and reach the electrode there, and the hole has to diffuse and reach the electrode here. So they must not recombine. So recombination rate must be low, and it must have long carrier diffusion lengths. And it must give me high open circuit voltage, because after all, for every photon, I'll get an electron and hole pair, which means I get 1 unit of charge flowing. But the total energy in that charge flow, current will be the same, but current into voltage is the power. So the total energy, the power is going to be controlled not only by the number of photons absorbed and separated, but also at what voltage they appear, and that there is an optimal value for maximize the power output for a normal solar cell material. What are the properties with respect to these? The good absorber of light, I said. The band gap of this material is in the order of 1.5, 1.6 electron volt. The ideal band gap for a material to absorb solar cell most effectively in the normal configuration is in the order of a little less than 1.4 electron volt. So it's very close to the ideal band gap. Why do we have an ideal band gap? It's very easy to understand. Let me give you a quick 1 minute detour of explaining why you need an optimum band gap. If the band gap is large, you get the open circuit voltage is controlled by the band gap, right? Because you cannot get a voltage that's larger than the band gap. So you increase the band gap, you increase the voltage. But as you increase the band gap, the photons coming from the sun, which have energy smaller than the band gap, will not be absorbed. So your current will go down. In order to maximize the current, you can make the band gap very small. So then you can go to almost limiting to a 0 band gap. All the photons will be absorbed, but then the voltage will go to 0, and so the power output will be 0. So you can see both in the infinite band gap limit and 0 band gap limit, you get 0 power output, which means necessarily mathematical requirement is that the power must be maximum for an optimum value of the band gap in between. And that depends on the solar spectrum. And since the solar spectrum is maximum in the order of, in that range, as I say, and from some very detailed balance calculation, it turns out the optimum gap is about 1.4 electron volt. And this has about 1.55 electron volt gap, this particular material. So it absorbs most of the solar spectrum. And it absorbs with extraordinary efficiency. It has an absorption coefficient which is extremely high. It has very long carrier diffusion length, hundreds of nanometers. And it has high voltage, open circuit voltage up to 1.1 volt. So it looks like that this material was ideally made by nature to give us high photovoltaic efficiency. And if that is all, then there is nothing more to understand. So the question is that all? Have you understood everything that is to be understood about this material? And this is where I'll start to show you some of our results after defining the issues, the open challenges that still remain to understand this. And the result that I'm going to show has been contributed by several generations of students, postdocs, and projects and UG students. So it gives a great pleasure to show all their names here. And we have also extensively collaborated with groups at JNCSR, and their names are shown here. And the Vienna group are doing, and L'Aquila group via the Vienna group, for some very fancy, very high-level, extensive calculations that I'll touch upon, not deal with it much, but these are the collaborations that I am very happy to tell you about. But the work that I'm going to talk about mainly is due to these two spectacular students, group members that we had, Sharda, Dr. Sharda, who graduated and is now a postdoc at Israel, and Bhushan Kore, who was a postdoc in our group and is now doing his second postdoc in Stockholm University. or KTH, in fact, not Stockholm, KTH. And they published a series of papers which are referenced here, and those references are given in the abstract, so you don't have to worry about it. And then also the calculation part was driven by this particular young researcher, Mendo Bogdan, and 2 papers were published here. And there's more recently Ashutosh Mohanty, who has just submitted his thesis a couple of days ago, who did some fantastic work on this system further, carrying forward Sharda's results. And he has published this particular paper, and there are many unpublished results. I may not have time to talk about those things today, but our understanding is certainly enriched by Ashutosh's work as well. The material that I'm talking about, as I have already said, is methylammonium lead halide. This X is a halide, mostly iodine, but it can be also bromine and chlorine. It is arranged in a perovskite structure. Perovskite structure is very easy to think of. Think of a cube. At the cube corner, you put this lead, which is called the B-site metal. You put the B-site metal at the cube corners, and the edge center, you put this halide X here, which could be iodine, bromine, or chlorine. And this A side that is occupied by this particular inorganic material, methylamine, you put it in the body center position, which is the A side. And that makes you the essential structure, perovskite structure. And you can see the structure can be described as this PB coordinated by 6 iodines around it, giving you PBI6 octahedron. And this octahedron is connected corner shaped because this one is common between this octahedra and the octahedra that is around there. Similarly, this is connected to the octahedra on that side, and this is connected to the octahedra on that side. So it's basically a 3-dimensionally running chain of octahedra in all 3 directions that makes the 3-dimensional network. And it is stabilized by putting in this void body-centered position this methylammonium or particular organic molecule. There is, in fact, the original perovskite structure has an inorganic material here, and you can put inorganic and a few organic materials here. And this is the methylammonium, and we'll often abbreviate it, call it MA, such that it will then stand for MAPBX3. Now, one very critical thing to keep in mind is this methylammonium is an asymmetric molecule. See, it's CH3 and H3. It's not CH3, CH3. As soon as it is asymmetric, that means it has a dipole. It is non-centrosymmetric. Non-centrosymmetric, and it has a dipole. So if these order, they can order either in a ferro fashion, aligned, so that the intercrystal structure will be non-centrosymmetric, and the entire system will have a polarization because the dipoles are going to arrange, and that means it will be ferroelectric, or they can arrange in such a way that one dipole and the next dipole cancel each other's dipole moment, which is called the anti-ferroelectric arrangement, and then it will recover its centrosymmetry in the crystal structure. That's why Sharda very early asked the question, is it a polar structure? That means, does it have a center of inversion or not? Do the dipoles align, or do the dipoles anti-align with respect to each other? Why should anybody be interested in that? There's a very fundamental reason why this is a crucial question if you want to understand photovoltaic applications. Why? I told you the standard photovoltaic device looks like this. It has this PN junction. So what I'm showing here, this is the electrodes, and this is the band diagram in between. This is the valence band, and this is the conduction band. Such that if in this part of the device I create an electron and hole, the electron will go there, hole will go here. And if I am close to this part where these bands bend, you can see that electron will drop down this way and go that way. But the hole will not drop down because the hole wants to be here, because the whole lowest energy state is here. Hole going there would be high energy state. So automatically, if I create an electron and a hole in this region, the electron goes there, the hole goes there, and the electron and hole get separated. And that is what is being shown over here. An electron and hole that are generated in this region of the PN junction will get separated. But if it gets generated very far away, then that will not happen because it doesn't feel the potential, which would mean now the electron and hole will drift very slowly towards respective electron. Hole will have to be drifting this way. This electron that doesn't find the potential yet will be diffusing randomly, and only when it senses that slight potential that it drives it, it will go that way. In the meantime, if that means it will take a long time, it will have chances of recombining the electron and hole or get trapped by many defects. And that's why you need to make the system as defect-free as you can, otherwise they'll act as trapping sites. And so that's the reason you want to make it very thin, such that the PN junction covers most of the material. But then if your material doesn't absorb, you cannot make the device thin. So you have a contradiction between the two. Device must be good absorber so that you can make it thin, such that this PN junction potential is felt everywhere and you have an effective separation. But imagine if your material was actually a photovoltaic material, a ferroelectric material. A ferroelectric material has an internal polarization, which means the conduction band and the valence band across the domain runs like this, such that it doesn't matter where you create the electron and hole. If you create the electron and hole here, electron goes there and boom, it goes down there. The hole goes up. You do here, the hole goes up, electron drops down there. So there's an internal potential everywhere in the material that separates the electron and hole. And that's why you can see these big, long arrows suggesting that if you had a ferroelectric material, then the photovoltaic effect would be actually aided by this tremendous internal potential. And that's the reason there's a whole school, a whole network of activities where people are trying to make photovoltaic materials out of ferroelectric material. Unfortunately, most of the ferroelectric materials, the band gap is very large. And as I told you, band gap has to be optimum. So the ferroelectric materials have not proven to be good photovoltaic material. But here is a chance. This material has a band gap of 1.55 electron volts. And it has dipoles inside. Can it be ferroelectric? In fact, the actual thing is a bit more complicated because you don't make a single domain device. You'll have your material will be a thick enough material, not a single domain. So ferroelectric domains will be pointing in all different directions so that it will not drive your system all the way to the electrode. The electron will not go all the way there. What would happen? Imagine that you create the electron and hole here. Electron goes there, hole comes here. Hole will climb up there, electron will climb down there, so that it doesn't matter where you create the electron and hole, the hole will go and sit at these top positions and electrons here, so that they are physically separated across this domain very quickly. And then we'll find the path along the domain boundary, which minimizes the energy for the hole and which minimizes the energy for the electron, and then they'll follow different paths avoiding each other, and therefore the efficiency will go up in a ferroelectric material. So that's why it's very important to understand whether the system is polar or not. So we come back to that same question, what makes this material so good? Is it ferroelectricity? In addition to the properties that we understand, because there is a dipole associated with M. So the question that we are really asking, are the dipoles ordered? They don't have to be ordered. If they're ordered, they can be ferroelectrically ordered or anti-ferroelectrically ordered. Or it can be disordered, and if it is disordered, it can be static, like in a glassy state, or dynamic, as in a paraelectric state. There's a more fundamental question, because if it is ferroelectrically arranged, it will have to have a non-centrosymmetric or polar space group. So the crystal structure, is it polar or not, the question that Sharda had asked, actually begs this question, which is more fundamental than the question whether it's ferroelectric or not. And unfortunately, when we got into this field, there was no clear answer to this question. So this is one question that we'll ask. The other question, which is fundamental, is the excitonic binding energy. I am talking about the electron and hole gets generated when a photon is absorbed. But this electron and hole get generated locally at the same site. And then they feel their attraction, Coulomb attraction, because one is positively charged, the other is negatively charged. And there's an associated binding energy, and that binding energy is called the excitonic binding energy. If the excitonic binding energy is very large, then the electron and hole will not like to get separated and will get very poor photovoltaic property. But if it is small, they'll get separated very easily. So it's a very important parameter to quantify the efficacy of photovoltaic material. But the estimates range from 2 to 100 millielectron volt. Now, the question is whether the excitonic binding energy large or small. Whenever I ask that question, that means I have in my mind a comparative point, larger than what, smaller than what. What that scale is the thermal scale, room temperature thermal scale, which you know is about 30 millielectron volts. Even if it is twice that much, let's say 60 or 70 millielectron volt, the thermal energy will be enough to split it apart quite frequently so that they can diffuse again. But if it is going to be 100 millielectron volt, then it's too high and it will not separate. And if it is 2 millielectron volt, then it will always separate. So the estimates that are available in the literature straddle the most important confusing range of the room temperature thermal energy range. And so it doesn't tell me why this material is good and why does it have such wide range of estimates. So that's also very confusing. So let me try to address these open questions for you in the remaining 15 minutes or so. And I start with the crystal structure, asking the question, is it polar or not polar? Before saying that, I should point out to you that there are phase transitions, and these are first order phase transition where crystal structure changes. So if I'm asking about crystal structure, I must define the temperature. In fact, it's easy to designate the temperatures where the crystal structure changes, and that is indicated by this DSC scan. You can see that above about 331 Kelvin, it has some crystal structure. In this range, which is the most important one, room temperature and somewhat above, and all the way down to 160 Kelvin, it has another crystal structure, and below that it has another crystal structure. The crystal structures are also very well known, and there's no controversy. This useful crystal structure is tetragonal. The low temperature structure is orthorhombic, and the high temperature structure is cubic. We know that. But all of these can also be polar and non-polar, and this is the information that was available to us when we went into. Starting from 1987 to 2015, everybody talking about the same compound, Na2Bi3. Three different phases, I told you, the low temperature orthorhombic phase, the room temperature tetragonal phase, the high temperature cubic phase. And different symmetries are here, space groups are written down here that were concluded by different workers. We don't have to pay too much attention except for the color coding. Whenever the color is red, that claims to be a polar structure, and whenever the color is black, it's a non-polar structure. This has centrosymmetry, and that does not have centrosymmetry. And that means for any given structure, the low temperature structure, somebody says it's a polar structure, some say it's a non-polar structure. For the room temperature, important phase, tetragonal structure, some say it's a non-polar structure, some say it's polar structure. Even for the cubic phase, some say it's non-polar and some say it's polar. So there was no agreement, and we looked at the single crystal X-ray diffraction very carefully, and we came to the conclusion that all of them are actually non-polar. Now, the reason this confusion exists in X-ray diffraction, which is also actually a limitation of our work, is that this polar and non-polar, the entire question is connected to MA. PBI3 is essentially non-polar, the cube that I showed you. It is the MA that is a non-symmetric, asymmetric molecule, and if it arranges itself, it can arrange in a non-centrosymmetric way and can influence also this structure. So it is essentially related to this. But this has only carbon, hydrogen, and nitrogen, and they don't scatter X-ray very strongly, and therefore X-ray structure determination is not a very good sensitive way of trying to figure out what MA is doing. So one needs to do other things. And so we started asking directly the question, let us try to sense what the dipoles are doing. Now, in order to understand what the dipoles are doing, what we looked at is directly, if it is ferroelectric, let us ask what ferroelectricity is characterized by. Here, what I'm showing you is that what is the polarization of a ferroelectric material if I apply an external electric field and sweep the electric field. I start with zero electric field. In x-axis, I'm showing the applied electric field. I apply the electric field up to something like 100 kilovolts per centimeter. I reverse it, go to minus 100 kilovolts centimeter, and come back to zero. And what the polarization does, first of all, very important to see that it has a large polarization even when I don't apply any external field. So there's a remanent polarization. That remanent polarization goes up a little, shows a hysteresis, closes the loop, and beautifully does this. This is exactly like in magnetization. You have a BH loop. A ferromagnet will show you a BH loop. A ferroelectric will show you a PE loop, polarization versus electric field. Here is another very well known. This is PZT, this is barium titanate. Again, you can see very clear loop of PE loop. Here is another, it is from our work, but not Sharda's. It is actually on inorganic perovskite. These are ferroelectric, and the reason we were excited about it, because we showed that you can minimize, lower the band gap almost down to the optimal band gap region below 2 electron volt by making barium titanate doped with some manganese and niobium. But what, for the purpose of today, I'm showing you that as long as you have a ferroelectric, you have this beautiful ferroelectric. Now let's go and apply this technique to our material. Now, first of all, we don't see the loop, but before I say, aha, it's not ferroelectric, I draw your attention to the fact that I'm holding the material in the low temperature phase. The low temperature below 160 Kelvin, we actually know there is general agreement that those dipoles on the MA, this methyl ammonium, are anti-ferroelectrically coupled, such that I get only the paraelectric response from the PBI3 cage, and this is the typical ferroelectric response where the polarization is essentially linearly changing with the applied electric field. Applied electric field this way, polarization this way, and there's an essentially one single line going up and down. The slight loop that is opening up comes from lossiness, which is a technical aspect. I'll not go into that. This is a measurement at 77 Kelvin. We are interested in the room temperature phase. What happens to the room temperature phase? Here is the data. You can again see it has nothing like a PE loop. It looks like a paraelectric, much like this, a little more lossy, so the loop is opening up a bit, but it is essentially proportional polarization to the electric field. That tells the PE loop measurement clearly says it's not ferroelectric. In fact, one can look at even more fundamentally whether it's polar, because all ferroelectric are polar material, but some of the polar material does not have to be ferroelectric, and this is a rather interesting point, but I'll not digress into that. If anybody wants, I can tackle it separately. But there's a very sensitive way of knowing whether a structure is centrosymmetric or not. If it is centrosymmetric, it's non-polar. If it is non-centrosymmetric, it is polar. The way it is done is by second harmonic generation. Basically, if a crystal structure is non-centrosymmetric, it's optically active, such that if you pump in enough photons of a certain wavelength, 2 photons get combined into one single photon with half the frequency, half the wavelength, twice the frequency. So you'll find that you pump in photon of a certain wavelength, and there are some photons that are coming out with half the wavelength. It is called second harmonic generation, which is a fundamental property of a non-centrosymmetric material. So we did this experiment, and this experiment, there are some technical aspects which has been dealt with in this particular paper in detail, because many people did the experiment wrongly. You have to choose your wavelength coming in very long. We used 1800 such that the second harmonic, half the wavelength, 900, is still below the absorption edge. This is the absorption edge. So we did this experiment, and what we find is shown over here. Let me walk you through this. This is the response from my material of the second harmonic generation. What I'm doing is just counting the number of photons coming out around the 900 wavelength, nanometer wavelength that I expect a peak to be. You see that when I use urea, which is actually well-known polar material, I find this beautiful second harmonic peak. Quartz is also known to be a non-polar, it's a polar material, but less efficient than this. This also shows me a peak. So I know exactly what is the width of the peak and where the peak should be if it is a polar material. My material is here, which has some huge intensity, but no peak here. In order to inspect whether there is a peak here or not, I'm plotting this whole thing in log scale shown over here. And you can see it's a smooth line going through. There's no sign of a peak here. I can fit a smooth line, subtract it out to look for the peak more closely. And I do that. And after subtracting a smooth line from here, this is the line that you get signal. And if there will be second harmonic peak, it would be positioned here, and its FWHM will be that much. That I know but from my test sample of urea and quartz. And you can see there is absolutely no second harmonic generation within the noise level, such that we can put an upper limit on the second harmonic generation activity, which is less than 0.02%, whereas standards have 27%. So you can see there's a 4 orders of magnitude limit that you can put on the nature of it not being a polar material. But there's an interesting twist to that. So we have said that, okay, it's not polar, but you see, these dipoles are there. This cage is PbI3, and this colored dumbbell of 2 different colors showing the asymmetric molecule methyl ammonium. Imagine that they are free to rotate. They have not aligned themselves, and they are free to rotate. Now, when they're free to rotate, I come in and create, for photovoltaic purpose, a high energy photon comes and creates an electron and hole. A dipole has a positively charged end and a negatively charged end. What would happen? The electron will feel attracted to the positively charged end, and the hole will go to the negatively charged end. And so the dipole will effectively now get rigid because of electron hole are trying to hold on to it to minimize their energy being attracted by the dipole. So it will try to freeze a dipole, and one frozen dipole will try to freeze another dipole. So it can happen that though in the ground state, the dipoles are not ordered, but this electron and hole coming and sticking to the dipole at 2 ends of the dipole and holding it there can propagate and create a transient ferroelectric state, which then can help photovoltaic. How can I probe that? In order to probe that, what we do is that we create this electron hole excitation. Before this can de-excite to any channel, we come in with a delay in time with our long wavelength and look for if it is producing any short wavelength photon, while the electron and hole are still alive in the material. And I can delay this change, I can change this delay time from 100 femtosecond or less than 100 femtosecond all the way to up to nanosecond. I know that the electron and hole live for several nanoseconds. So down from 100 femtosecond to up to nanosecond, if I look for if this half the wavelength photons are coming out or not, I would know whether this electron hole is giving rise to temporally transient ferroelectric material. I'll give you only the conclusion. We have done this. These are the data that concludes that this is the signal that we get second harmonic generation, which is essentially the noise. The 0 level is drawn by dashed line for all these MAPBR3, MAPBR3, CSPBR3. The reason we look at CSPBR3, instead of MA, we have put cesium, which has no dipole. So we know what is the level of the 0 signal should be, and that provides me the 0 signal. And you can see that all of these are only noise, and there is no second harmonic generation, even transiently. So there is no transient ferroelectricity that is getting generated. So I will, I am running out a little bit of time. I still have about 5 minutes. Can I assume another extra 5 minutes?
Yeah, yes, sure, please.
Okay,
Please.
Okay, so about 10 more minutes and I'll finish up. So what are these dipoles doing? They're not ordering. So what are they doing? That is the question that we're asking them. In order to understand that, as I said, low temperature, we know that they antiferroelectrically arranged, but at room temperature, the structure is centrosymmetric. Each dipole is not centrosymmetric. So time average description is centrosymmetric. So what are the possible dynamic behavior? One is that it's rotating freely and independently every dipole. Another possibility is that it's rotating in a correlated manner. All the dipoles are seeing each other and holding hands rotating together. Or they're not rotating at all. They're frozen, but randomly frozen, such that there is no order associated with them. And so I don't see in the crystal structure any non-centrosymmetricity. How can I separate these different possibilities out? It turns out that looking at the dielectric property gives us a clue. There's a very busy curve. I'll quickly tell you, walk you through stepwise. First, I want you to look at this particular part, and which relates to CSPBBr3, whose structure is shown over here. The most important thing to note is that this Ma that was at the bottom center position, I've put cesium ion. So there is no dipole. And then the dielectric constant looks like this. So when dipoles don't contribute much to the dielectric constant, the dielectric constant looks like this. Now I'm going to replace that cesium with MaPbBr3. That's what I'm going to look at, and that is this one. At the low temperature, where I know if there is an antiferroelectric ordering such that dipoles don't per se contribute to the dielectric constant, you can see it looks more or less like the CSPBBr3. And that is because the dipoles are not contributing. But look at this part. There's a huge dielectric constant, and not only that, it is increasing as 1 over T. As I lower the temperature, it is going up, just like a free dipole should be. In fact, one can in detail model this and fit this to find out the dipole moment and the rotation, and that is done over here, but those are technical aspects. I'll not go into that. But basically, this 1 over T dependency shows that the dipoles are freely rotating. Whenever one is freely rotating, one has to keep in mind what is the time scale I'm talking about. If anything is rotating at 1 second rotational speed, if you look at it with time scale of 1 year, it will look like a freely rotating. If I look at it with a millisecond, then it will not look rotating. So it really depends on the probe. The probe, the fastest probe we use is about 1 megahertz, which is like 1 microsecond. That means down to about 1 microsecond, it looks like freely rotating. So it is rotating at a rotational speed much faster than 1 microsecond. The same story of MaPbI3, you can see 1 over T dependency. There's the antiferroelectric state and looking like CSPbI3, and there's MaPbI3 Ma rotating. Again, much faster than 1 microsecond. And this is where we did extensive MD calculation in collaboration with the Vienna group. And the estimate that we found from there that it rotates at 6 picoseconds. And no wonder that when you look at it with 1 microsecond, which is like 1 million times slower of 1 picosecond, so it looks like freely rotating. So these are rotating at a 6 picosecond in the order of a few picosecond rotational time scale. That brings me to the last point that I've promised to talk to you about, is the excitonic binding energy. Now, excitonic binding energy, if it is small, it will be very good. If it is large, it will be very bad. If it is comparable to the thermal energy, it will be all right. As I said, that there is no consensus. There's 2 to 100 millivolts, all kind of estimates. Like here, you can see 6 millivolt, 98 millivolt. These are all different publications at different times. The way, one of the technique of finding out is to look at the photoluminescence coming out. Because what happens if an electron and hole generate and they're coupled by an excitonic binding energy, they will decay. But if you provide it enough energy so that the excitonic binding energy is overcome and the electron and hole are decoupled, then they'll move apart, and so the photoluminescence event will not take place. So as I increase the temperature compared to the binding energy, exponentially I excite this excitonic state into the free electron hole state. So the PL emission intensity will have an exponential dependency on temperature, and it will become lower intensity at higher temperature because the excitons are breaking apart. And this can be formalized, and expected dependency of the photoluminescence intensity as a function of temperature can be given by this, where you can do exponential dependency, and EB is the excitonic binding energy, essentially the barrier that you must overcome with the thermal energy kBT to break apart an exciton into a free electron and free hole. So all that you need to do is to measure the photoluminescence as a function of temperature, fit it to this equation, get EB. Sounds very simple, and sure enough, if you do the experiment at function of temperature, you can see that wonderfully there's a very strong dependence. At room temperature, it is here, and as you lower the temperature, it is going up so rapidly. So I should be able to extract the binding energy from here. Except for the problem is, you take the same material and make measurements on different days, different years, different students, different proclivities, and you get different kind of dependency with the temperature. Which means the binding energy, if I fit it and try to extract from here, all of them will give me different kind of binding energies. What is going on? Why is such a thing happening? We realized, and this was seen by other people also, there's a fundamental problem. In order to do the experiment of photoluminescence with changing temperature, you want to put your sample on some cold stage whose temperature can be changed. Now, when you lower the temperature, you don't want the sample to remain in air because then everything will condense on it. So what you do is to put a vacuum shroud around the sample and evacuate at the surrounding of the sample so that it is clean, remains clean. We didn't start to cool down the sample. We did this setup and started evacuating. As a function of evacuation, we found that the emission peak is getting quenched very rapidly and emission intensity becomes almost completely zero very, very quickly. This emission intensity area that I've shown you a spectrum here is plotted over here, and you can see how rapidly in a log scale, mind you, if I did it not log scale, you would have seen it going down vertically, absolutely. In a log scale, it becomes less than 1% very, very quickly. That means something's going wrong when I evacuate. What is something going wrong is believed to be that as you evacuate, actually two things can happen. For doing this measurement, I'm evacuating, so it could be evacuation time, but also I'm shining light on the sample. So maybe shining light is degrading my sample. So there, this time, which I've written as evacuation time, actually both evacuation time and exposure time of light. How can I separate the two out? I can do that by doing an experiment intermittently, where I switch on the light, do an experiment, put it into the dark, don't do the experiment, again switch on the light, do the experiment, and keep alternating. And here also I find exactly the same trend, and whether it is dark or light, it follows exactly the same smooth curve, suggesting that switching off the light is not helping me at all, which means what is putting it down is this continuous evacuation time that the system is feeling. And the reason it happens is that there are adsorbed material on the surface which apparently passivate some defects, typically oxygen and some amount of moisture that are sitting on the surface of this material and passivating. Normally, dirt does not passivate, it kills the photoluminescence. But this is a very unusual material where the defects are partially passivated by this. And as I pump these very loosely bound passivating agents, they get sucked out. And then these defect states become active. And when I create electron and hole, and remember, this electron and hole are getting created very close to the surface because this material has extraordinarily high absorbance. Remember, I celebrated the fact that it has very high absorbance, but that becomes its doom today because all the photons are getting absorbed very close to the surface. And on the surface, I have this defect state sitting, and they trap this electron and hole that have got generated. They provide lower energy states than the excitonic binding energy. And so that exciton gets split, and then they transfer themselves into these states and become dark. And then there's no photoluminescence happening. Okay, having understood that, now how do I do my experiment? Because I need to have photons go in, but the photons will get absorbed at the surface. I need to evacuate to be able to change the temperature. But if I evacuate, my passivation goes. I need to somehow do the absorption deep inside the material so that even if I evacuate, which will affect near the surface, will not affect my absorption and photoluminescence process. And this can be done by doing what is known as a two-photon absorption technique. So basically, you come in with a photon whose energy is less than the band gap energy. So one photon doesn't get absorbed. But you have sufficient number of photons such that at times, two of the photons combined simultaneously make an electron hole pair. Since this has absorption probability that is very low, absorption coefficient that is low, your entire system, bulk of the material is uniformly illuminated, and the signal comes from throughout the bulk of the material. And when it combines and a photoluminescence happens deep inside, it comes out and it doesn't sense the surface defects. And you can do safely the experiment. And that is how we did the experiment. And you can then do the temperature variation. It's NAPBI3, two-photon absorption induced emission experiment. You can see the excitation is at 1200 nanometer, which is a very long wavelength, lower than the band gap of the material. And then you can plot the intensity variation. Then you can fit it to an equation, and therefore you can extract the excitonic binding energy. Reliable excitonic binding energy, different samples, different times. One is 55 millivolts, another is 48 millielectron volts, typically telling you what the error bar is on these measurements. You can do it on MAPBBR3 when it has a crystal structure change from cubic to tetragonal. You can see also the excitonic binding energy changes across it. You can do it for FABBR3 and others also. In fact, together with Vienna Group, we had long time back calculated the excitonic binding energy for all useful materials that were being talked about at that time. These are calculated from very, very sophisticated, most sophisticated calculations. And their MAPBI3 is shown over here, 45 millielectron volt, FAPBI3 35 millielectron volts, FAPBBR3 60 millielectron volts, MAPBBR3 71 millielectron volts, etc. And if I put our experimental data on this, you can see experimental data is here, very close to the calculated value. And here, these two are very close to the calculated value. This experiment corresponds to this value. So there's a very good agreement and consistent set of excitonic data that we have got. And that brings me to the end of my talk. Before I end, allow me to do a quick advertisement of, okay, let me first summarize the conclusion, what I've shown today with a long introduction, why we are excited about it, and there are many more things that still continue to excite us. I said that there are open issues about that we had addressed. Crystal structure, we conclude that it's non-polar. Ordering of the dipole, we said that it doesn't order at the room temperature phase. It's dynamically disordered, rotating with a time scale of about 6 picoseconds, and antiferroelectrically ordered largely at low temperature. Excited state also doesn't give rise to any ordering. And the excitonic binding energies, these are the materials that we have estimated, and these are the values. So having concluded, I'll quickly advertise one of the journals that I think is very exciting. And if you are working in this field or any field related to energy research, then you should seriously consider. One of the good thing about it is that the publication time from submission to publication is typically about five weeks, which is one of the fastest. So the decision is typically in under 3 weeks that you get, and publication in about 5 weeks time. And it has, if you are interested in impact factor, it seems to have a fairly high impact factor also. With that, let me end this talk. Thank you for your patience. Thank you. I'm going to stop the projection now so that I can come back to the normal mode. And if I need to come back here, I'll project again. Thank you.
So thank you, Professor Sarma, for such a interesting talk. It was quite beautiful. Now it's a time for questions.
There have been questions, Pankaj, already.
There are questions in the chat box.
Yes.
Chat box, there are questions.
So should anybody want to?
Yeah, can I read it?
Yeah, it'll be better if you moderate.
Yeah, so there is a question from Pralay Kanti Santra. If he's here, he can ask question directly. Pralay? Okay. So he's asking. Yeah.
Did you mention that the space charge region for PN junction, it can extend up to several hundreds of nanometer, whereas in case of ferroelectrics, it's only up to maximum up to 100 of nanometer. So typically, what happens then, if the absorption coefficient is not very high, then the material is not going to the ferroelectric photovoltaics is not going to be helpful. Do you have any comment on how ferroelectric photovoltaics?
Okay. I went over that a little fast. Let me go back and tell you why it still does. I actually sort of anticipated this question and put a slide there. Let me show that to you quickly. I assume that you can see my slide?
Yes.
Okay. So you look at this last one that just appeared now, this one, you can see? Okay?
Yes.
Now, there are many domains. You can see, right?
Correct.
And each of these domains will act independently. Now, wherever in this domain, if you create, what will happen? The hole will go there, electron will go there. If you create in this place or in this place, away from the electrodes, hole will come here, electron will go there. So basically what happens, it doesn't matter in which domain you create, immediately it goes to the two ends of the domain. So each domain now separates. Now once it separates, now think of these that the different domains of a ferroelectric material. Each domain is much shorter than the electrode dimension or the separation. But the pathway now are completely non-crossing. And so it gives rise to better efficiency of connection.
Okay.
That is the reason.
Thank you.
Why. Besides the fact, another thing that I have not gone into, that you can get the open circuit voltage that's larger in principle because of the polarization can add on some small value to the open circuit voltage. But that I didn't go into, that gets too technical.
Sure. Thank you, Didi.
Next question.
Yeah, can I ask? This is PK Giri.
Yeah, please do.
Yes, sir. Yeah. So this ferroelectric thing, I was thinking whether we can apply the polling technique for such material, which are well known for the non-centrosymmetric and other like even the quartz people do it. Usually at high temperature, even though this material is not good for high temperature. So then it can improve the photovoltaic efficiency, I believe.
Yeah. See, the comment is, see, this is where that subtle point that I talked about, because it's a general talk I didn't go into, that polar need not be ferroelectric. So polar, basically the difference is that you cannot switch non-ferroelectric polar material. So there are polar materials that are not ferroelectric. But you can, going to higher temperature, you can pole it. This is exactly what you're saying, and then lower the temperature and have the finite polarization survive.
Yeah, freezing.
You're trapping it into a metastable state. But for that, you need, first of all, a polar material. This material, if you try to, the problem is, if it would be a glassy material, the glassy state would allow you polling.
Okay.
But a non-glassy, paraelectric state does not support polling, because there is no metastable state also possible.
Now, with light, it should be possible.
No, basically the point is that if you have a paraelectric state, as soon as you remove the external stimulus, the applied electric field, it will randomize itself. Because it's these dipolar units, the MA units, are free to rotate. If they were stuck in random directions, you take it to high temperature, give it some amount of rotational freedom, then you apply a huge voltage to pull it, and then you freeze it down, it will remain frozen because that's in a deep metastable state. But a paraelectric state where dipoles are at room temperature freely rotating, almost barrierless rotation, you'll find that it will always depolarize itself, even if it's cold at a high temperature. Because basically, in order to hold at a temperature and then freeze it down and retain that, you need a deep metastable state, a large barrier, right?
Okay, disordered, maybe disordered.
A large barrier to transit from the metastable state to the stable state.
Okay. Thank you very much.
Didi, Biplab has a question. He is watching through Facebook. So I am actually.
Biplab, my God.
Yeah, Biplab.
Now I'm getting nervous.
Yeah, so he has a question for you.
Pranay has asked, Anshuman was there. I mean, I'm now in deep trouble.
So Biplab's question is 6 picosecond time for molecular dynamics.
Yes, 6 is, okay, take it as 1 to 10. What is the question?
So is it done in the excited state with electron-hole interaction?
Yeah. This is a DSC calculation. This is Biplab. This is absolutely the top of the line. It's Chris's group, and it was done with a DSC in the excited state. Not only that, in fact, that is not enough. It turned out that unless you take very large calculation, these don't converge with respect to K points. And the calculations were horrendous. Okay. I hope Biplab got the reply.
Yeah, I hope so.
And if he didn't get to it, he'll get back to me. He won't let me go so easily.
Okay, I think there are more questions in that chat box. One from Anamul Haq. So he asks, do you have any evidence for the non-centrosymmetric crystal structure of MAPBX3?
There have been claims. See, the point is, our point of view is that it is centrosymmetric. So I will not like to volunteer any evidence of non-centrosymmetricity. But in many publications, so this is a confusing point. Why do people sometimes believe that they get SHG signal? Some believe that they're seeing a PE loop. I would not like to criticize those. These are all cited in our papers. You can go and look up those. We believe that they're making some mistakes, because of which they are coming to that conclusion. But the ones that we have looked at, MAPBX3, are all centrosymmetric. They are not.
Sir, I have the doubt is, sir, see, you are doing the measurement below the room temperature. And
no, room temperature also, depending on what we are doing. Yeah, go on.
So these are in orthorhombic phase.
No. So, I have shown you data for all temperatures: orthorhombic phase, tetragonal phase, cubic phase for crystal structure, X-ray diffraction. I have shown you PE loop measurement, both at 77 Kelvin, which is orthorhombic phase, as well as room temperature, which is tetragonal phase.
Yeah.
I have shown you dielectric measurements, which shows that it's not ferroelectric like dielectric data over the entire temperature range. So I've shown you SHG, I have shown you at room temperature.
Yeah. The interesting thing I would like to say, sir, that you have shown that cesium, when you replace methyl ammonium by cesium, it is not showing you the dielectric constant. But there is a paper recently came in JAX 2020. So it shows that CSPB BR3, this they shows that non-centrosymmetric because of the cesium ion is shifted from the center part of the perovskite, and they are showing actually this ferroelectricity, and they have given the evidence for that.
That is under a strain film, if I remember right. Is that correct?
Yeah.
I should not comment unless I can recall the detail of it, but there are that will take it into another domain altogether. If I apply strain, what would happen? Okay. So often I cannot comment on it. I think some vague recollection I have of strained material showing some signature of ferroelectricity, but again, I reserve my opinion because unless I do the experiments or I'm convinced of the experiments that are reported. Because remember, even MAPBI3 or many of these materials, they apparently show SHG in some of the experiments. And there are very respectable journals where these are published. So the journal is not an evidence. The experimental data is an evidence, and I need to critically evaluate it before I say it.
Thank you.
Okay, then there is Dr. Samir Sapra. If you you can ask the question directly.
All right, Didi. So there we go.
Now is your chance.
Wonderful presentation. Really loved, enjoyed listening. I wanted to understand the 2-photon experiment. Why it's the vacuum is not playing a villain over there?
That's simply because the surface is the problem, right? So when the photon is emitted, after that there is no problem. So if the recombination takes place far away from the surface, so basically the exciton is created spatially separated from the surface at a far enough distance inside the bulk, then the propensity for it to be, the transfer probability of the exciton breaking and giving one to the surface state is more. Basically, you're now depending on the exponential dependence on the separation that dictates the wave function overlap, which will control the transfer probability into the surface states.
Okay.
So that's the reason. There are many.
The intensities are anyway very low over there.
The intensities, of course, I mean, it's the two-photon process.
Right. Another one, if I'm allowed.
Yeah, sure.
Does this methyl ammonium, does it have a very low dipole moment?
No, methyl ammonium has a huge dipole moment, but Fa has very low dipole moment. I did not, okay, so quickly, that is a very interesting. Dielectric constant data really shows very interesting, gives insight. Yeah, allow me quickly to show you that since you asked this question and I didn't show you the data. Let me show you the data. No, where the hell is that? Where it is? Here. Wait. That's not the right one. I'll do it in a very short time, but there's a comparison slide. What am I looking at? Okay. Okay. Here, what I am comparing is FAPBCl3. This is Sharda published in JPC. FAPBCl3 with MAPBCl3. Red is the MAPBCl3 and this one is FAPBCl3. This jumps up due to some transitions. See that as long as I have MA, I see this 1/T dependency. Do you see that?
Yeah.
And that comes from the dipole contribution. FA doesn't show any dipole contribution of that kind. That reason being, we had actually wrongly interpreted in this particular paper, saying that maybe FA is not rotating because we didn't see this response. But later we understood that MA has dipole moment which is 10 times larger than FA. This is about 1D and this is about 0.1D. And the dependency, this proportionality constant, is square of the dipole moment.
Okay.
So the contribution coming from the dipole moment from NA to an FA is 1:100. And that's why you don't see the evidence of dipole here. And what you're essentially seeing, non-dipolar contribution to the dielectric constant in FA. And this part is actually because MA is active. You see this very strong deviation in this range. Once you get into the orthorhombic range where the MA gets frozen down and doesn't have this rotation that changes the direction of the MA dipole, you get back the same dielectric constant.
Right.
Okay?
Okay, thank you. Thanks.
We have a question from Krishnanjan Pramanik, whose microphone is not working. So he asks, how about the toxicity of lead? Can it pose any risk in large-scale application?
I guess as much as your lead-acid battery will. I mean, there's not a... I mean, this is just to make sure that you understand the question that you are asking. Lead is toxic, but that is not to say that lead is not being used. Every car battery is full of lead, right? So this is to say that we should not use these kind of arguments to offhand and very irresponsibly reject any idea. First of all, science is interesting, even if it is dangerous. Otherwise, you will not think about the actinides at all, or radioactivity at all, or hydrogen at all. It's dangerous. So there's interesting things, but application, of course, one has to worry about it in the long run. There are ways to contain it. Lead-acid battery over the years, technology has evolved such that there's no problem. We know how to recycle it to a very large degree, and we are living with it. So if we can address other fundamental issues of using it as photovoltaic material, this will see technological application, even if lead is there. But it's a concern that one should not forget about. one should not trivialize the concern, and one should not trivialize the important fundamental and technological excitement of a field.
Yeah, there are two other questions, one from Pranay Nandi. If you are there, you can ask the question directly. If you are not, then we can read it out. Okay, it says, ferroelectric measurements were performed on polycrystalline pellets in the presentation. However, literature report both polar and non-polar behavior from electrical measurements depending on the sample synthesis conditions. Does crystallinity of hybrid perovskite affect this measurement? What is your opinion regarding it?
Yeah, again, these are serious questions and difficult to answer. I personally do not believe that there is the problem of polycrystallinity, because we have measured also on single crystals. Because as I told you that all our X-ray diffraction work is on single crystals, we can make large single crystals, and we have done actually dielectric measurement as well as PE loop measurement on single crystals also. The results are similar. And we have measured other groups, some group that believed it to be ferroelectric, their single crystal data with our measurements, and showed them that the data is consistent with not being ferroelectric. So our belief is that it's not ferroelectric. Cases where people have seen or claimed to see ferroelectric material or properties, if you look at it, the PE loop measurement that they report, at least I have not seen any PE loop measurement that is clean. Most of them are extremely dirty PE loop measurements, and in fact shows such a lossy feature that any traditional scientist involved in ferroelectric research will never accept it. Okay? That's a very strong statement I'm making, and I'm making it with full sense of responsibility. Then there is second harmonic generation technique, where also people have seen, mainly with microscopic measurements, spots that seem to have second harmonic activity. If you read our viewpoint article in ACS Energy Letters, we have pointed out what are the pitfalls there. What are the cares that you must take before you can claim? Because those cares were not taken. This is not to say that experiments are wrong. I'm saying enough care was not taken in some of those experiments, we can point out. So my sense is that I have not seen any result in the literature published which convinces me beyond any reasonable doubt that these have anything to do with ferroelectricity.
Yeah, that's another question from Harishankar Shuman. You can ask yourself if your microphone is working.
Yes, sir. Yes, sir. Sir, what about stability in ambient conditions and now? Why not commercial?
The stability issue has been addressed substantially. Of course, it's not like silicon, but I really am not the best person, but I know several thousands of hours. I don't know what is the champion cell right now, but to me, it looks like the people are actually very serious scientists involved in this, are very serious about commercial application, which tells me that they think that while the stability issue is a concern, but it is surmountable. It is not something that's a showstopper. I won't be able to tell you the number, but some of these very high efficiency ones are also very stable, people have reported. How much stable, for how long, what is the loss of efficiency? Often I don't remember, because my ability in that direction is actually extremely limited. Because if you see, I have not even made a single cell in my life. I work with only pure material and try to understand the material property. So that's a disclaimer. So I really am not the best person to say that. But my sense is that people believe, and there are fantastic scientists are putting their money, literally money, they're investing money in opening startups to start production using this technology. So that convinces me that they believe that there is future in it.
Thank you, sir. Because many morphology engineering has involved due to stability nowadays.
Yeah. So but that is the part I have not come to. Most of the stable ones are actually with various doping at the A site, and that's a totally different talk, another 1 hour talk. And that's what Ashutosh, his entire thesis is on. I was saying that Ashutosh has done fantastic work, and he's the one who's trying to understand the stability of those materials. And he's found some very surprising results. One is already published in ACS Energy Letters, you can look it up, but here's some more results.
Okay, Pankaj, over to you.
So any other question?
Hello.
Yeah, please go ahead.
I am Suvash Saha from Vidyasagar University. First of all, I like to thank Professor Sarma for his wonderful lecture. So, actually, I was associated with the cultivation of science. We are expected as a director for the institute. I was a long back ago. Okay, so I remember that occasion, and
then I wouldn't have given this talk today. Anyway, ask your question.
Okay, so it's a wonderful talk. So first of all, I like to congratulate for your wonderful discussions and the very illuminating scientific information. So you have given the answer that I have a queries that whether you have developed any device or solar cell with these your wonderful materials of the perovskite. So you have said that you have not made. So I was interested about the efficiency of the device.
There are some people who are working in that direction in the country. You can either look up, search, or if you have difficulty, let me know through an email. I'll put you in contact with some of those people if you're interested in that. I mean, Satish Ogle is there, Dinesh Kabra is there. These are people who are device sort of people. I know Anshuman Nag is also doing some devices now. There are many people. Somaputa Acharya also does cultivation, you mentioned. He does some devices. There are several people. I'm sure I'm missing many names, and it's not should not be taken as an offense against anybody. But you know, right at this moment, these are the names that I can rattle off for you, that you can contact.
Thank you, sir.
Thank
you.
So any other question? So if not, let's thank again Professor Sarma for such a beautiful talk. And it was really quite elaborative, and the way he painted the talk, I think many of the students would have got the idea that how do one approach for a particular problem and go into deeper and deeper in aspect of that. And so it was really a great learning moment for all of us. And so with this, we would again like to thank Professor Sarma for his time and giving such a elaborative presentation. And sometime when the things become normal, we would definitely like to see him here in IIT.
Oh, I'd love to come to your campus. I mean, it has, I think only once, and Giri, because Giri is there, I have to admit that once I couldn't come.
You can twice, if I remember correctly.
No, not twice. Only once I missed coming.
2010, there was a conference on strongly correlated materials that was organized by Dilip Pal. So Indro was here. You came briefly for a day. Your flight was terribly delayed, if you remember. You were supposed to give the talk in the morning. You landed in the afternoon.
I was saying that I've got only one invitation. So if you invite, I'll be there. You can be sure.
So the other time you remember was that ICANN that was organized by Giri.
Yes. I have very fond memories. Then at the academy meeting, I was there, and I was there for for the FIST evaluation. So I've been to your campus many times. I love it, and I'll definitely come back.
Yeah.
I'll get you back again, and our students, if they can meet you in person, I think that's.
I'd love to interact.
Thank you very much.
Thank you very much.
Thank you very much, Professor. Okay.